Hello, everyone. Today we're going to talk about rotation. And when we're talking about rotation, we must also talk about moment of inertia. Inertia is an object's resistance to changes in motion. So, and it's proportional to mass. So, the more massive an object is, the more inertia it has. So, in other words, the more difficult it is for it to accelerate. And when we're talking about rotation, we're talking about moment of inertia, which is resistance to changes in rotational motion. So, moment of inertia, if friction is force between two surfaces that opposes motion, inertia is not a force, but is a resistance that exists in an object with mass to changes in its motion. Inertia is proportional to mass in such a way that the bigger the mass, the greater is its inertia. Speeding up or slowing down a massive object requires more force than doing the same for an object with less mass, according to F equals ma. The greater the mass, the smaller the a, and the greater must be the force to overcome to increase its velocity or change its velocity. That's Newton's second law. Moment of inertia is the resistance of an object to changes in rotating or spinning motion. It has the same concept, except that instead of translating motion, it involves angular motion, angular momentum, instead of linear momentum in a straight line. So when we're talking about moment of inertia, we're talking about its relation to rotation or spinning, um, as opposed to translation motion, where translational motion is when an object is moving in a straight line. If an object is making a turn, then it has rotational motion. Newton's second law derives from its first law, which is the law of inertia. A point object with mass m rotating around a center at a distance r has a moment of inertia equal to mr squared. So if you have a point mass going around a circle, and if you know the distance from that point mass to the center of the circle, the moment of inertia is mass times the radius squared. Objects can be of different shapes and densities, so in order to calculate its moment of inertia, there needs to be a summation of all of its point mass particles rotating around the center of the axis of rotation. So if we know that the moment of inertia of a point mass is mr squared, being m its mass and r its distance from the center, if you have an object with an irregular shape or whatever it has, you can think of each atom, you can think of each particle as point masses. And as the object rotates, it's all the point masses rotating around that common center, which leads to the total moment of inertia of the object. That is when integrals may be necessary for complicated objects and surfaces. The object on the left has an irregular shape, so the moment of inertia is the sum of infinitesimal mass elements around the axis of rotation. The right-hand rule is used where the thumb should point in the direction of the arrow. So if you want to demonstrate a rotation here in physics, the thumb should point in the direction of the angular momentum vector, where the four fingers point in the direction that the object is rotating. So you just go like that. Okay, if the axis of rotation becomes different, there is a different amount of inertia, which explains why it may be easier to spin an object one way and not the other. If you change the axis of rotation, instead of the object rotating around its center of mass, if it's rotating around one of its edges, then the moment of inertia will be different. It can increase or decrease, which is why for an object it might be easier to rotate it one way as opposed to the other way. Here is the moment of inertia for some objects. The arrow points um, from the axis of rotation. So we have a ring rotating around itself. We have a cylinder rolling. We have a rod rotating about its center of mass. We have a rod rotating about its end. We have a solid sphere rotating through its center of mass. And we have a spherical shell. Notice, however, that the spherical shell has more moment of inertia than the solid sphere. That's because all the mass of the shell is concentrated on its surface. And whereas in a solid sphere, the mass is more spread out, which leads to less moment of inertia because a great portion of the mass is closer to the center. And that's not what we see in a shell, where all the mass elements are on the surface of a shell, which means they're all in the same, roughly the same distance from the center, which causes the moment of inertia of the shell to be greater than the moment of inertia of a solid sphere. Moment of inertia is resistance to changes in motion. The greater the moment of inertia, the slower it takes the object to speed up and the slower it takes to slow down. So if an object has a lot of inertia, it takes a huge amount of force or a greater amount of force for it to accelerate. And if you apply the same force to an object with less inertia, you're going to see that the second object will accelerate more because there is less inertia. So the smaller the amount of inertia, the faster it takes the object to speed up and the faster it takes to slow down. When going down ramp, the object with the least amount of inertia will reach the ground first since it speeds up more. Yes, so the object with less amount of inertia will pick up more speed because it's easier for it to accelerate. When going up a ramp, the object with the greatest moment of inertia will reach higher since it takes longer to slow down. Since it takes longer for an object to slow down with more inertia, the object with a higher inertia, higher mass, will actually go up, will reach a greater height if it's going up an incline or and so forth, because inertia is resistance to changes in motion. When an object is rolling towards the top of an incline, up an incline, the acceleration is for it to slow down due to friction and gravity. But because if the object has more inertia, that means that the object would take longer to slow down, which means that the object with the higher inertia will reach up higher on the incline. When a force is applied on an object at a given distance from the pivot point, the axis of rotation, it leads to a spin or rotation. Of course, if you have the pivot point and you apply a force perpendicular to that pivot point at the edge of the object will rotate. The equation for torque is the perpendicular components of force times distance from the axis of rotation. So here we have the equation, Fd sine of theta. It's the perpendicular, it's the component of the force perpendicular to the length of the object. In other words, sine of theta. If theta is the angle between the force and the axis through each and the horizontal line where the object is or force. So basically, the angle theta would be the angle between the force and the distance from the pivot. In this case, the pivot is towards the left, so the angle is between the force applied and the distance from the pivot. And of course, if theta is 90, it means the greatest amount of torque can be done is applied to the object as it rotates. Where F is the force, D is the distance from the pivot point, theta is the angle between the distance and the force, I is the moment of inertia of the object, and A is its angular acceleration. So torque is equal to moment of inertia times angular acceleration, which is different from linear acceleration. Angular acceleration is radians per second squared. In statics, torque is used to create structures whose net torque is zero. So if the net torque on an object is zero, it means the object will not rotate, or if it's already rotating, it will maintain the same angular speed. The net torque on the machine on the left is zero since counterclockwise torque, 30 times 1, balances the clockwise torque, 10 times 3. I did not include g in the equation because g on both sides would cancel, which means that the object is in static equilibrium. So it's not going to move, or if it's already moving, it's going to maintain the same angular velocity. Um, the momentum of an object moving a circle or making a turn is equal to the angular momentum of an object. So the angular momentum is equal to the moment of inertia times the angular velocity. MVR if you use linear, velocity. It's mass times velocity times r, being r the radius, the distance from the object to the center of the rotation. Similar to linear momentum, angular momentum is conserved in a closed system, where no energy is lost due to friction and other deceptive forces. So in physics, we have conservation laws, we have conservation of energy, we have conservation of momentum, and of course, we also have conservation of angular momentum. When an object rotates, it has kinetic energy from the rotation, which is equal to 1/2 moment of inertia angular velocity squared. So if an object is rotating, it also has energy from the rotation. When an object is moving through space, let's take Earth, for example. Earth has kinetic energy due to its motion through space, and it also has rotational kinetic energy from its spin motion, because it's spinning around its own axis. Conservation laws is what allows scientists to mathematically explain natural phenomena and make some predictions even within probabilities. Usually, conservations involve ideal cases, which are not how real matter and energy works in our universe, but which facilitates human understanding of the cosmos. Conservation is seen in energy, mass, charge, linear momentum, angular momentum, and in many other cases. The loss of energy in the universe and its diverse natural phenomena is what causes its rise in entropy. If the universe is entirely closed, however, this energy is kept within its barriers. And if not, then the universe leaks energy, which could be the proof that we live in a multiverse. So basically, if we think of energy conservation, the fact that the entropy in the universe is steadily increasing because time can only go forward. You see a plate break on the floor when you drop, but you don't see the little pieces coming back together and becoming a plate again. That's because the universe tends to greater disorders, right? The disorder always increases in the universe, being entropy, the amount of disorder. So now, however, if energy is not leaking out of the universe, if energy is well confined within the cosmos, then the entropy would technically remain the same in the cosmos. But if energy is leaking, then the amount of disorder is in fact increasing. We in physics, we believe that the entropy in the universe is in fact increasing. Things tends to be in a state of greater disorder over time. But we haven't seen the edge of the universe yet, and we yet don't know if the universe is infinite or if it's finite. We assume it's finite for mathematical reasons, so we can make predictions, so we can explain all of reality. But the truth is, we just don't know. Similarly to how F equals ma, force equals mass times acceleration, torque is equal to moment of inertia times the angular acceleration, where I is the moment of inertia of an object and a is its angular acceleration radians per second squared. Similarly to how work for an object in translational motion is Fd cosine theta, where F is the force, d is the displacement, and theta is the angle between the force and displacement. The amount of energy placed on a rotating object is thus work equals the torque times change in theta. So notice that when you apply force to an object and it moves forward, you're applying a force over a displacement. So that's work, that's the amount of energy put into the object. But if you apply a torque on an object and the object rotates a given amount of theta, this then gives you, this is then an explanation for how you're putting energy on the object so it can rotate. Torque is also what leads to change in angular momentum over time, which means that following. Since torque is moment of inertia times angular acceleration, torque is also moment of inertia times the change in angular velocity over the change in time. And if we multiply the time times the torque, we get that torque times the change in time during an action is equal to the moment of inertia times the change in angular velocity. So here then is the brief explanation of rotation in physics. And I will get in more details in further videos about the proofs for moment of inertias and proofs for all of these equations that I've shown and demonstrated here in this video. Thanks for watching.